This is the last topic in which we will discuss how to separate and identify certain organic compounds. So in this topic, you will learn about the spectroscopy, and it can be infrared spectroscopy. So in a spectroscope, or the second thing, you will learn about the chromatography, the separation technique. Now, spectroscopy, in which we are using electromagnetic radiations such as infrared, microwaves, or radio waves. So in infrared spectroscopy, what we use in infrared spectroscopy, basically we use infrared radiation that cause the bond stretching or vibration within the molecule. So using this, we can identify the type of the bond which is present within the structure. Using the microwave, we can cause a bond breaking. A certain molecule absorb microwave. It can cause them to rotate also, and it can also break the bond. Even UV or ultraviolet radiation as well. Radio waves, what is the effect of the radio waves? Basically, what these radio waves will do for a magnetic material, like example, if any atom, any element is a magnetic, so that will act like a domain. Means if we have external magnetic field, say north and south, so magnetic field is always pointing from north to south. So if a molecule is placed, so the molecule will align according to the external magnetic field. But when we pass this infrared, radio waves, so radio waves absorbed by the molecule and it will flip the molecule because it absorb energy, so it is having higher energy. So it flip the molecule opposite to the direction of the magnetic field, and after some time it release that energy, so we can identify the hydrogen environment or the magnetic environment within the molecule. This technique we'll discuss in detail. The first thing is the effect of different type of radiation on the molecule. Then we have ultraviolet radiation, UV radiation, as you studied in AS chemistry, that free radical substitution reaction which occur between the alkane and halogen such as chlorine or bromine. The first step is the initiation reaction. And how this happen? The ultraviolet radiation cause a homolytic bond breaking. The bond will break, the each chlorine will take its own electron and it will form a chlorine free radical. So these are some effects of the radiation. Infrared radiation, because they can cause a bond vibration, so using that we can identify the type of the bond. The microwaves absorbed by certain molecule, we can also rotate the molecules using microwave. Radio waves can be used for rotation or vibration of the hydrogen which are present within the structure, and ultraviolet radiation can cause the bond breaking or initiate a chemical reaction. NMR, nuclear magnetic resonance. N stands for nuclear, M stands for magnetic, and R is stands for resonance. Basically, what is NMR, nuclear magnetic resonance? As you can see, the structure of the hydrogen consists of one proton and around the nucleus there is electron which is revolving around the nucleus. Proton, a charged particle moving, also electron, a charged particle moving. So whenever charged particle move, what it create a magnetic field. So basically this hydrogen will behave like a magnet, which we also called a domain. So what happened? Basically, when this hydrogen is acting like a magnet and we apply the external magnetic field, like we have magnetic poles, North Pole and South Pole. And if we place this hydrogen or a molecule which is having hydrogen, so that hydrogen will align according to the magnetic field, external magnetic field. Then we use radio waves. So when these hydrogen absorb radio waves, they have more energy, so they will align opposite to the external magnetic field. But they cannot remain aligned for a longer period of a time. So re-radiate, they return back to the original position and re-radiate that energy. So how much energy is released by these hydrogen? We can use this energy to conclude how many hydrogen are present in the environment, and the intensity of the radiation will show us like how many hydrogen are, like how many hydrogen environment. Using this we can identify how many hydrogen environment and number of hydrogen in each environment. So example, if you have a and this NMR is divided, nuclear magnetic resonance is divided into low resolution and high resolution. So we will discuss both of them, low resolution and high resolution. First, what happened in low resolution, like example, if you have CH3, CH2, and CH3. So how many hydrogen environments are there? So this CH3 is one hydrogen environment. Then CH2 is another hydrogen environment, and there's another CH3, but that is not the different environment like we check the neighbors also, because for this CH3 next is CH2 then CH3, and for the second CH3 next is CH2 and CH3. So basically both of these CH3 are identical, like they have identical neighbor. So if I say this is one hydrogen environment, this is also the same hydrogen environment. So this is hydrogen environment A and CH2 is hydrogen environment B. So how many hydrogen environments are there? There are two hydrogen environments. So how many peaks we will get? We will get two peaks. The number of the peaks shows how many hydrogen environments are there. And how many hydrogen, like the relative intensity, 3 and 3, 6. There are 6 hydrogen in environment A and there are 2 hydrogen in environment B. So what is the simplest ratio? The simplest ratio will be 3:1. So when we obtain this spectrum, one is for CH3, another one is for CH2. So what will be the intensity? So we will get 3 centimeter example, then the other one will be 1 centimeter. So one of them is due to CH3 and the second one is due to CH2. This is peak A and then peak B. Now, what are the labels of the axis? Y-axis is about the relative intensity and x-axis is known as chemical shift. What is a chemical shift? Chemical shift is a comparison with another molecule, inert molecule, compared to that molecule, how much they are magnetic. That's known as a chemical shift. That's in the next slide we'll discuss. But this is the introduction of NMR, nuclear magnetic resonance. So what we do, we first apply external magnetic field, which cause the atoms, the hydrogen, because why the for the other atom we did not mention any magnetic field, because maybe, as you know, the other element is carbon. So what carbon contain? It contains 6 proton, it contains 6 neutron and 6 electron. So probability is there or a chance is there, maybe it may be a magnetic, may not be a magnetic. That's probability. But for hydrogen it is always a magnetic, because you have proton and electron, only two particles are there, so less likely they cancel out the effect of each other. Is it clear how to identify the number of the hydrogen environments and how this technique works? Any doubt in this? So example, how does the number of the charged particle affect? Because what happened, when the particles are moving or spinning, they produce magnetic field in opposite direction. So maybe what happened, like one proton is moving clockwise, another is anti-clockwise, so they may cancel out the magnetic field of each other. But in case of hydrogen, the proton is there, which is inside the nucleus. So only one particle is there inside the nucleus. So that's why there is no other particle to cancel out the magnetic field of this proton. But like if you're taking carbon is having 6 proton. So what happened? One is moving clockwise, another is moving anti-clockwise, so they may cancel out the effect of each other. Then example, there are different molecules, as you can see, and this one is high resolution NMR, but we are discussing first low resolution and then I will explain the high resolution NMR. First, when you check this one, how many hydrogen environment? There is high resolution and there is low resolution. But first thing, I'm explaining low resolution NMR. So CH3, this is one hydrogen environment. Then this is a second hydrogen environment, CH2. And this is a third hydrogen environment. So 3 hydrogen environment, that's why 3 peaks will be there. And what will be the relative intensity? For this hydrogen environment, it will have 3. The second hydrogen environment is 2, and the third hydrogen environment 1. So what does it mean? It means that one will be 3, if 3 centimeter, 2 centimeter, and 1 centimeter. And what about the location, the place, like where I will have a peak of CH3, where I will have a peak of CH2, and where I will have a peak of hydrogen for OH? That for that we have to use the data booklet. You can see the next slide. These are the chemical shifts. If OH is there, that will be from 0.5 to 5. Like this is a range in which you can draw. If CH3 is there, which is attached to alkyl group, 0.7 to 1.2, you can draw in this range. If NH2 is there, which is at R means alkyl, like carbon chain is there next to it, from 1 to 4.5. If alkyl group, CH2 group is there, next to that is alkyl group, so 1.2 to 1.4. If CH is there, next to that is the 3 carbon chain, then 1.4 to 1.6. But you don't have to memorize this. What you have to do, you have to use a data booklet, and using a data booklet, you can work out. So when you check another molecule, like this molecule, as you check, the name, this is ester basically. So when we worked out, we have CH3, CH2, so the structure, I will draw the structure again. Look, you have CH3, then CH2, then C double bonded with O, then C, H3, CH3, and CH3. Now, how many hydrogen environments are there? You can see these CH3s are identical because next to them is the same height. But this CH3 is different. Why it is different? Because next to this is CH2. But for all these CH3, next to that is carbon. So they are identical. So if I say this is A, then this will be B, and then the CH2 will be C. So how many hydrogen environments are there? 3 hydrogen environments. And what will be the relative intensity? Like in this hydrogen environment, 3 hydrogen, then 2 hydrogen, and then total 3 plus 3 plus 3. So total 9 hydrogen. So when you have the peaks, you will have 3 peaks. What will be the relative intensity? One will be 3 centimeter, another one is 2 centimeter, another one will be 9 centimeter. And what about the position? Like which position you will have? So you like this is CH3 and next to that is CH2, carbon chain is there. So when you check this chemical shift for CH3, so where you find CH3 for which next to that is a carbon chain, so this is CH3. So you will get from 0.7 to 1.2. The height will be 3 centimeter or ratio will be 3 compared to other peaks, and the range is from 0.7 to 1.2. You can draw this. Then the next one, is CH2, and this CH2 is C double bonded with O, and then CH2, and next is a carbon chain. So you have to check for CH2. This is for ketone group. This one is for ether, like O is there and CH. C double bonded with O and C. So you can see this one CH because C double bonded with O, but that is connected. This is not connected with oxygen, this is connected with a carbon. So C double bonded with O. This is for ester group. See this R is there. So which one we will get? Because next to this CH2 is the carbon chain is there. If the carbon chain is there, so next to that, like 2 carbon groups are attached. So you will get a peak from 1.2 to 1.4. And what about the third one, the CH3? For CH3, for which the carbon chain is attached, it again you will get from 0.7, but that's for that is for the first one for which the carbon chain is attached. This one is CH3, next to that a carbon chain and O is there. So we will get a peak from the range. This is C double bonded with O, carbon is there with oxygen, and then hydrogen is there attached to that carbon. So that will be 3.7 to 4.1. Like here you can see as you can see, like if we take this ester, so this ester is having CH3, CH2, and CH3. So 3 hydro environment, that's why 3 peaks are there. Then what about the position? This CH3 is from 1. The CH3 is there from 0.7 to 1.2, that one. Then CH2 is there. It's from, because if it is C double bonded with O and CH2 is there, that is from 2.4, like I 2.1 to 2.6. So 2.1 to 2.6, you will get that peak. And for the third one, the CH3 is there. So for this CH3, the peak is around 3.7 to 4.1. So 3.7 to 4.1. So we will get 3 peaks. The areas, you don't have the area of CH3, CH2 and CH is different depending on how many hydrogen environments are there. In a data booklet, you don't, the chemical shift will be there. The chemical shift is given, the range is given in the same way. Area, it does not show you area. Area is different thing. Area shows number of hydrogen present in each environment. The chemical shift is important, so you have to know, like if OH is there, that what will be the chemical shift. CH3 attached to alkyl group, what is the chemical shift? Area is not given. This is not the area, this is a position, the chemical shift. And what is a chemical shift? Chemical shift basically refers to compare to hydrogen, compare to tetramethylsilane, TMS, because the tetramethylsilane, its chemical shift is considered as 0. And why we use this? Because it is inert, unreactive, does not react, it is not toxic. So we use TMS or tetramethylsilane, and the where we get the peak of tetramethylsilane, that's a 0 of the scale. Then equivalent, then 1 will be there, 2, 3, and so on. So compared to tetramethylsilane, what is the magnetic effect of the molecule, the hydrogen environment, that we will use to identify how many hydrogen environments are there. And using the data booklet, we'll identify the chemical shift for each environment, and using a area, how to get the area of the peak is how many hydrogen environments are there and their relative intensity, that shows area of the peak. Like another molecule, you have CH3, CH and CH2. So how many hydro environments are there? 3 hydro environments. And what will be the relative intensity? Because in the first hydro environment, you have 3 hydrogen. In the second hydrogen environment, you have 1 hydrogen. In the third, you have 2 hydrogen. So relative intensity will be 3 is to 1 is to 2. And the position, to check the position, you have to go through the data booklet, like check where is the chemical shift for CH3, where is the chemical shift for CH, and where is the chemical shift for CH2. So as you can see, the chemical shift for CH is from 0.7 to 1.2. For CH2 is from 1.2 to 1.4, and for CH it is 1.4 to 1.6. But if you check for alkene hydrogen, which belongs to alkene, the chemical shift is from 4.5 to 6. So this will be from 4.5 to 6. So when we get the peak, like when we draw these peaks, so we have CH3, CH2, we have CH3, CH and CH2. CH3 is there. CH2, sorry, CH. So you can see you have to check like which one is R means carbon chain, then CH2. So for this hydrogen, it's from 4.5 to 6. So for this hydrogen, basically, because you can see it matches with, it will be from 4.5 to 6. You can draw in this range. Then this CH3, the CH3 is there 0.7 to 1.2. And this CH, which is having the carbon chain both sides, you can see the CH. So this is identical to the other one as well, because you have a carbon chain and then C double bonded with O, and other side also carbon chain. So in the same order or same range you will draw. The first thing is identify the number of hydrogen in each environment, and second is using a data booklet, identify the chemical shift. Like if you have another example, so CH3, CH, CH2, CH3. So when you check this CH3 with other CH3, so these two CH3s are identical because same neighbor, like 3 carbon, also 3 carbon. So these two are identical. That's why it's called A. Then this is B, then this one is C, and then D. So 4 hydrogen environments are there. So 4 hydrogen environment means 4 peaks will be there. And how many, the intensity of the peak, this is 6 hydrogen total. This one is 1 hydrogen, this one is 2 hydrogen, and this one is 3 hydrogen. So relative intensity will be 6. Like if one is 6 centimeter, then another one 1 centimeter, then 2 centimeter, and 3 centimeter. And using this, the chemical shift, like chemical shift for CH3, what is the chemical shift? What is the chemical shift of CH2? You will identify their positions. For this one, we have 2 hydrogen in 1 hydrogen environment only. Why 1 hydrogen environment? Because identical CH3s are there. For this one, 1, 2, and 3 hydrogen environment, and relative intensity 3 is to 1, 2 is to 3. For this one, CH3 is there, then CH is there, then CH2 and CH3. Why these two CH3s are not identical? Because the neighbor of this CH3 is CH, but for this one, the neighbor is CH2. So they are not identical CH3s. So that's why both CH3s are considered as different hydrogen environment. So that's why we'll get 4 peaks with a relative intensity of 3 is to 1 is to 2 is to 3. Is it clear? So first thing is identifying the number of hydrogen in each environment, like identifying the number of hydrogen environment, and second thing is using the area, using the number of hydrogen in each environment, we can identify the area of the peak. This is in low resolution NMR. But what happened in high resolution NMR? In high resolution NMR, the peak will further split into n plus 1 according to the neighbor. Like what we get, if you take this as, this is the first question. So we have A, B, C, and D. So how many peaks? Because there are 4 hydrogen environments, so there should be 4 peaks. So due to 4 hydrogen environments, in a low resolution MR, we will get 4 peaks. And what are the intensity of these peaks? Like one is 6 centimeter example, then 1 centimeter, then 2 centimeter, and then 3. But it is not like order, like first one is A, it is according to their chemical shifts. This is in low resolution NMR. But what happened in high resolution NMR? High resolution NMR, there is an effect which we call coupling. So due to this coupling effect, these peaks will further split. So, and it is always split into n plus 1 N is the number of neighbor hydrogen. Like for environment A, like this was environment A, environment B, environment C, and environment D. So for environment A, how many neighbor hydrogens are there? Only one. So if neighbor hydrogen is one, it will split into two peaks. Like it will further split into two sharp peaks. That one peak is split it into two. For environment B, how many neighbor hydrogen? 2 plus 3 plus 3. So 2 plus 3, 5 plus 3, 8. So it will split into 9. Like it will split into 9 peaks, the environment B, but not with the same height. Like the B's only intensity is 1, so it will split into 9 peaks. What about C? The neighbor 3 plus 1, 4 hydrogen, so it will split into 5 peaks. And what about D? The neighbors 2, so it will split into further 3 peaks. So basically, the number of the peaks remain same, but further splitting occur due to the effect which we call a coupling effect. Like coupling effect means that magnetic fields of the two hydrogen environments or neighboring hydrogen interact, which result in a further splitting, which we call coupling. How you will identify these peaks? So you have to learn the Pascal table for this. Maybe you in maths you studied this Pascal table, so you can see if neighboring hydrogen, if there is no neighboring hydrogen, 0, then how many it will split? It will all split into n, because the splitting pattern is n plus 1. So it will split into n plus 1. So 0 plus 1 is 1, or you will have a singlet. If the neighboring hydrogen are 1, so it will split into 1 plus 1, which is 2. And what will be the intensity of these two? It will be same height. Like ratio, relative size of the two peaks will be 1:1. If the neighboring hydrogen are 2, it will split into 3. And what is the relative height? 1, 2, 1. Like 1 centimeter, 2 centimeter, 1 centimeter. If neighboring hydrogen are 3, it will be like if 3 peaks are there, it will be triplet. If neighboring hydrogen are 3, then it will be quartet. And what will the relative intensity? 1, 3, 3, 1. And if neighboring hydrogen are 4, 4 plus 1, it will split into 5. What is the relative intensity? 1, 6, 1, 4, 6, 4, 1. How to learn this? It's not the difficult thing to learn. It's easy, like Pascal table. 1, 1, then 1, 2, 1, then 1, 4, sorry, look, first 1 is there, the Pascal table, then just add them like 1, 1 plus 1, 2, and then 1. Then 1 is there, 1 plus 2, 3, 2 plus 1, 3, and then 1. Then further splitting, 1, 3 plus 1, 4, 3 plus 3, 6, 3 plus 1, 4, and then 1. So this is the Pascal table you can make. 1, 4 plus 1, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, and then 1 will be there. So it's better you learn the for first 5, like the relative intensity or the splitting. So if you have a molecule, like example, we have a molecule such as methyl ethanoate. So in case of methyl ethanoate, first thing, how many hydrogen environment? This is 1, 2, and 3. So first we identify there are 3 hydrogen environments. So in low resolution, we'll get 3 peaks. In high resolution also, we will get 3 peaks, but these 3 peaks will further split. So for A, how many peaks it will split into? Because the neighbor are 2, so it will split into 3 peaks. So because of neighbor having 2 hydrogens, so it will split into 3 peaks. For CH2, the neighbor is having 3 hydrogen. Next is there is no hydrogen. So neighbor is having 3 hydrogen. So if there are 3 hydrogen, how many peaks it will split? It will split into 4 peaks. Quadrat. And for C, the neighbor is 0. If neighbor is 0, then how many peaks it will split? It will be only one, a singlet. So what we will get? We will get a triplet, a quartet, and a singlet. So these peaks, like the peak of CH3, the peak of CH3, which is having 2 neighboring hydrogen, so it will be triplet. A peak of CH2 will be quartet because there are 3 hydrogen, so 4 peaks will be 4. And the peak of another CH3 will be a singlet. So you can see the splitting patterns. For this CH3, the neighbor is having 2, so it will be triplet. So you can see a triplet is there. And when there's a triplet, that is considered as one peak, but this one peak is split into 1 is to 3 is to 1. That's why 1, 1, and 3. The CH2, for this CH2, the neighbors are 3. If neighbors are 3, it will be 3 plus 1 means 4 peaks will be there. And what is the distribution of the quartet? The distribution of the quartet is 1 is to 3 is to 3 is to 1. So like comparative ratio, like this is 1 centimeter 1, so this will be 3. And for this CH3, there will be a singlet. Why there is a singlet? Because the neighbor is 0 hydrogen. If 0 hydrogen, so 0 plus 1 is 1, so singlet will be there. And the total relative intensity, when we compare, this will be 3, this will be 2, and this will also be 3. So basically what happened, because this is having 3 hydrogen, this also having 3 hydrogen, but why they have different height? Because this is further splitted into triplet, and this one is remain singlet, so that's why it is much higher. Is it clear, this part? The high resolution NMR. The values on the x-axis is chemical shift. You have to use a data booklet to work out, like CH3, you can see CH3 is from 0.7 to 1.2. So 0.7 to 1.2. Then this CH2, the C double bonded with O is there. So that's from 2.1 to 2.6. And this CH3, the CH3 is from 3.7 to 4.1. That's why the chemical shift. According to a data booklet, you have to use this chemical shift.